Hey guys, Buildzoid here, and welcome to another successful hardware resurrection video. Though I'm not entirely certain that this was an actual resurrection, because I'm not entirely certain that the board was completely dead. I have a sneaking suspicion that even with the memory VRM in this condition, the board would still be able to turn on, you just wouldn't have these two memory channels. Now, I didn't try to turn it on in this condition, because I'm not sure that the VRM would be very pleased with trying to turn on with no inductors. And yeah, like didn't really want to risk the power stages like burning up if for some reason I'm not sure that they should burn up, but it's just, you know, if the I'm not sure what would happen if the inductors aren't where they're supposed to be, and so I decided I'm not turning the board on until they're back in place. Anyway, the board in question is a Gigabyte TRX40 Designare, and I picked it up on eBay for 145 quid, which is entirely too much considering TRX40 is a dead-end platform. Thank you, AMD. Very cool. And I don't have any use for TRX40 motherboards. That's actually sort of the bigger issue. Like, I'm not a big fan of the Threadripper CPUs. And yeah, I really have no use for a TRX40 board, but the thing is, I enjoy fixing things just for the sake of fixing things, so I regularly go to eBay just looking for dead hardware to pick up and try repair. And the thing is, like, this right here was just, when I saw this, I got really excited, because this, you know, like I saw this and I was like, I can fix this with like 99.99999% certainty, which is not true for a lot of the other stuff that I pick, dead stuff that I pick up on eBay, especially dead GPUs. Well, okay, now let's go motherboards first. So dead motherboards. If you don't have a very obvious hardware failure somewhere, like a dead VRM or something, motherboards are a nightmare to troubleshoot, because there are so many controllers on motherboards, right? You've got your chipset, you've got your Super I/O, you've got the audio stuff, you got the USB controllers, you got the SATA controllers, you got the like some boards come with external controller or like embedded controllers, and you just have so much random junk on a motherboard that can cause it to not function properly that it's really frustrating to try fix them. Just if they have any other failure than like missing power rails or something like that. And also you can get motherboards where like the chipset is dead, and then you're kind of screwed. Or there are certain motherboards that use like rebranded controllers that you need like a very specific firmware for. So if you can't, like, you're screwed again. So yeah, motherboards are kind of like, I generally avoid motherboards unless they have some obvious, you know, like physical damage like this. Which is pretty rare. There's a lot of motherboards where it's like, oh, it doesn't turn on and there's no apparent reason for it. And then, of course, you have motherboards with pin damage, which is kind of boring to fix. Tedious and boring. And then with GPUs, like, GPUs are an absolute nightmare, because while they are much simpler than motherboards, it's not very uncommon for GPUs to have just complete silicon failure. Like, I've had, I've had cards show up with the core, like the actual silicon of the core being just completely shattered. So you're not fixing that, because the core is worth more than the rest of the card. I've had cards show up where the core is like, has an internal short circuit, and again, it's just like, okay, well, you're not really doing anything about that. You also get cards where like the VRM exploded and in the process killed the memory controller of the core or the core itself, and you're, again, just not fixing that. So while GPUs are much simpler, because GPUs are basically just some memory, the GPU, and a bunch of power delivery, it is, in my experience, not super rare for GPUs to be very, very dead. So, yeah, and so this is not like the worst purchase I've ever made as far as dead hardware on eBay goes. That would probably be the dead RTX 2070 that I picked up that has an internal short circuit on the core. So, you know, yeah, this right here was just like it's a TRX40 board, not exactly what I was looking for, but this is one of those kind of like it's not the simplest of fixes, right? There's some like, this is relatively involved to get back up and running, but it's not a motherboard that could be like impossible to repair. And so I bought it because I was bored, and when I get bored, I look for stuff to repair. Even if I have no use for it. Like, I really wish this was an X299 board or something, but nah, it's TRX40. Anyway, the board is now functional. As you can see, here it is. You can see that the inductors by the 24 pin are at very wonky angles, and there's also a new capacitor there that isn't supposed to be there. So yeah, board works. To test it, I've mostly, like, I still want to take an oscilloscope to both of the memory power rails just to make sure that, like, the one I repaired isn't running, like, way noisier than the other one. But the thing is, I need to take that measurement from the back of the board, and just involve, like, that's a relatively involved process to set that up. Also, I'd need to shuffle around one of my test benches, and so it's just like, yeah. For now, what I've done is just set up a memory overclock on this, and this is actually the best, like, stable memory overclock that I've managed to get on a Threadripper. So this is 4400 CL16 with 1620 1626, and like the crazy thing is, this actually, well, we're not going to get into too much detail about this overclock, but the crazy thing is this is currently the second fastest. Like, if I posted this setup's Y-Cruncher score to HardwareBot, it would be the second fastest 3960X score for Y-Cruncher. The first fastest score is also mine. So, yeah, unfortunately, the 3960X just didn't really get a lot of attention on HardwareBot, so it's not like there's a whole lot of competition for getting first place in Y-Cruncher with a 3960X. But technically, like, I hold first place, and this setup right here also holds second place. The other setup was on liquid nitrogen, so that's why that was faster. Anyway, the goal with this memory overclock was basically just to run something that's like high speed, because like with high memory speeds, you actually increase your power consumption just because power consumption is basically linear with memory speed. And then it's also at high voltage. It's over 1.6 volts on the memory right now, which is just to, put some load on the power delivery. And yeah, it passes, 400% mem test. It runs 44 loops of LinPack 10 gigabytes. So yeah, I do have a fan on the memory sticks on the on the backside of the board, because the VRM that runs, like, the VRM gets kind of warm, and then the memory sticks get warm, and then everything gets unstable. Also, like, I don't think the exhaust from the actual CPU cooler itself is that much of an issue, because the air passing through the actual fin stack, that's hot, but that fan is sitting really low on that air cooler, and actually so the first stick from the CPU socket actually gets, like, relatively fresh air, at least in, like, the lower part, because there's, like, a bunch of cold air coming in between the heat pipes. But the other memory stick is probably not getting any airflow at all because of the first memory stick, like the memory stick in front of it. Anyway, so yeah, like, the board clocks memory great, and maybe I'll do a video, actually I'll probably do a video going into more detail about the memory settings, because it was kind of interesting to set this up. I also kind of want to try get the TRCD-RD down, because TRCD20 is disgusting to look at. I don't think it's going to come down very much. The memory controller just generally is really bad at TRCD on this CPU, which is really not that surprising. Like, a lot of CPUs struggle with TRCD, but this one struggles, like, a lot. Like, normally, like, I'd be annoyed if it was like TRCD 18, but, like, this didn't do TRCD 19 initially. But there's some differences in the voltage settings from when I first started setting this up, so yeah, I don't know. There'll be another video about the memory settings. The main point is the board runs, it clocks memory fine. As far as I'm concerned at this point, it's fixed, or resurrected, if you will. So now let's talk about the actual repair process. I decided that I've come to the conclusion that it's easier to just take photos as I go through the repair process of a board. So, yeah. Let's go through that. So here's a close-up of the actual memory VRM. And also, I guess I should point out that this is a TRX40 Designare revision 1.1. And the difference between a revision 1.1 and a 1.0 is that the 1.1 boards and also there's like 1.2 and 1.3 revisions. These all have a better memory VRM. I am not entirely certain why. Maybe it's because Threadripper, like, yeah, I'm not sure why. The memory VRM is more substantial than what you get on most Gigabyte DDR4 boards. Like most Gigabyte DDR4 boards, you get 2 low-side MOSFETs, a high-side MOSFET, and like a cheapo single-phase rich tech. I think it's an RT8120D VRM controller with built-in drivers. But this right here, yeah, we have a Renesas RAA2290001, which is a fully digital, like, multi-phase VRM controller, and then you get these two SIC 651 Vishay DR-MOS components, and I think these are like 50 amp DR-MOS components, which is just like totally overkill for memory power delivery, but yeah, for whatever reason, Gigabyte felt the need to like upgrade the memory power delivery. Maybe the Threadripper memory controller is just kind of a like power hog. I really don't know, because like all the other DDR4 boards from Gigabyte with the like they had some early ones that were using like 2-phase 40 amp or single phase 40 amp power stages, but I think since like Z270, they've just been using, you know, three like discrete MOSFETs and a cheap VRM controller for everything else. And I've never had any issues with like the B550 or the X570 boards when it comes to memory overclocking. So this is rather interesting that they decided to switch over to this. And this brings up one of the like complexities with this repair, because we've sort of got 3 different problems to solve here. One, obviously, the inductors are not attached to the board, so we need to get those back on the board. But one of the like details that's kind of annoying is that you see this ripped out trace, and the same thing right here, and the same thing right here. Well, that's the current sensing connection. Because this controller uses the DC resistance of the inductors to measure how much current is going through each of the phases. And so basically the way it does that is you just have a connection to like directly to the legs of the inductors. Like it does just connect straight to the memory power plane. It's not fancy. There's not like or it's not fancy. It like from a perspective, it's not really that fancy. It literally like one end of the current sense, you know, connects to the output of the memory VRM. It is supposed to connect very directly to the leg of the like the output leg of the inductor. And that's not really a leg, that's a pad, but whatever. And then the other one is supposed to connect to the like switch node side leg. So you can see like that's why the current sensing is connected like right down the middle, right? So that it connects primarily to the inductor and it's not connecting to like the switch node too much. Like it arguably, if you connected this side of the current sensing, say over here, to like this corner of the switch node, you would get like inaccurate current sensing measurements. So that's why it's where it is. I don't really care that much about having super accurate current sensing, because again, this is memory power delivery. It really shouldn't be pulling that much power. I wonder, wait, I want to check. Is there a great big, oh, actually, it might be really, so this right here is probably the input filtering for the memory power delivery. So if I wanted to, one of the ways you could check the memory VRM power consumption is you could desolder this inductor and like replace it with a shunt resistor, which would like include the power losses in the power stages, but like that would be an easy way to get a power measurement. That's like not super intrusive, because the other options are like, well, arguably you could also hook up to the controller. And actually, I might even have the correct dongle to talk to this thing. So I might look into that. I don't know. We'll see if I get bored of the motherboard. I probably won't do that. But yeah, like its memory power delivery, it really shouldn't need that much. Like it shouldn't need that much current, and therefore I don't really care that the current sensing isn't going to be super accurate. But this is one of the issues. We do need to reconnect the current sensing, because if it's not connected, I'm 99% certain that this will not run. The controller will be very upset if it doesn't have a current measurement. And so, yeah, that needs to get reconnected. And the third issue we have is, like, the switch node is gone. So we need to do, like, you're not realistically connecting an inductor directly to the, you know, output pins of a DR MOS component. Like, that's just not going to work. Just, like, look at that look at the pad on that inductor, then look at this, and yeah, that's not going to work out. So we're going to need to sort of rebuild that to some extent. And so, well, we're basically going to have to rebuild the switch node somehow. And so now let's move on to the actual sort of next step of the process, because that's the three issues I need to deal with, is like set up connection points for the output of the inductors. We need a new switch node, and then over here, well, on both of them need the current sensing reconnected. So step one, scrape off some of the solder mask. So you can see, and for that I just used a box cutter blade. This one's kind of dull, but it doesn't really need to be sharp, right? We're just using it to scrape off the solder mask. And on a lot of high-end modern motherboards, the solder mask is actually really tough. If you work on like older, like especially this matte black solder mask tends to be kind of annoying to scrape off. But anyway, box cutter, does a perfect, like the box cutter blade does a perfectly good job of that. Anyway, so I scraped off some of the solder mask here for the memory power plane. We do have these power vias for the memory VRM over here, and I decided that I'm not actually going to bother with those because I don't really think they're that necessary. Again, it's memory power delivery. Sure, the board originally had those connected, but I'm sure if we get I'm not too concerned about the current having a hard time like getting down into the inner layers of the board. Like the DIMM slots are through hole. The current can use the through hole pins of the memory slots for all I care. That might actually work quite well. I don't know. But yeah, I basically decided I'm not going to worry about these vias too much because they're kind of a pain to, like scraping the solder, because they do still have solder mask on them. So like scraping that solder mask off is just, it feels like you might accidentally actually remove the top head of the via, and then you're not going to have anything to connect to anyway. So I just kind of decided, whatever, I'll ignore those. Probably won't matter too much. And then over here, again, scraped off the power plane and scraped off the solder mask on the power plane over here, scraped off the solder mask on the current sense, and also did that over here. Also, you'll notice that these components right here, like they're awfully close to where the power plane got ripped out. So I did end up checking the resistance on these. Like there's really no reason that these would have any traces running through like this area of the board. But they are very awfully close to the damaged section of the PCB. So just in case, I did go ahead and check the resistances of all of these components, and they matched the resistances of these components. And I was measuring the resistance of those components to ground, as well as I think one of them is like the snubber circuit or something. So one of them I was checking against the actual switch node. Basically just took a bunch of measurements to see that, the resistances of these components and these components over here were like sensible values and not just completely way off. Anyway, so yeah, and so these all looked like all the measurements checked out fine, and so I just kind of moved on because these didn't get damaged by the power plane getting ripped up here. So up next, I added some flux. And the flux I use is ChipQuick SMD4300, and I have one warning for you if you're buying this stuff. I've had it come in two different colors with kind of different soldering performance, or more like soldering behavior. So this gold-colored flux is great. This stuff is awesome. It washes off easy. It lasts while you're soldering with it. It doesn't turn into like black gunk. And then there's the pale yellow version of it, and they both come under the exact same part number. Like, I went and checked my DigiKey order to make sure of this, because my first tube of SMD4300 was a pale yellow, and it was usable, but you needed to use a ton of it, because it would just burn up into black gunk super quickly, and it stopped being useful as solder. So you kept having to add more and more of it if you were doing any soldering, because it just didn't last. This stuff, on the other hand, does last, and so you don't need to use anywhere near as much. So that's nice. But the issue is, like, yeah, you can get two different flavors of this flux under the same part number, which is like, I don't know what the hell ChipQuick is doing with that. It's really kind of annoying. However, the thing is, this is sort of the easiest to get water soluble, no clean, tacky flux that, like, at least for me, And I really wanted a water-soluble flux because it makes makes cleaning boards so much easier. Like, I've had some, like, actually, when I bought this tube of SMD 4300, I also bought a different no-clean flux without the like, water-washable properties, and that stuff doesn't even come off with isopropyl alcohol, which, like, was a real surprise to me because I figured, you know, like, that would normal, like, yeah. So when it comes to choosing flux, definitely you want no clean, because if you have a flux that you have to clean off, then the issue is that means the flux is actually, like, corrosive even at low like, room temperature or low temperatures. And if you have a corrosive flux residue on your board, you're gonna have a bad day because it's just gonna slowly eat the board. So for electronics, you really do need to use a no clean flux, because if you use, like, pipe welding or pipe soldering flux, yeah, you're gonna have a very bad day with that. Then the tacky flux part, I'd say that's probably optional. I've only ever used tacky fluxes because, also, like, with the tacky fluxes, they're also good for, like, like, hot air soldering. Not that I'm doing any of that here, but yeah, you know, like, I do hot air soldering for other stuff. So yeah, I use tacky flux because of that. And then the water washable part, this just makes it a lot easier to clean. Like, this stuff comes off with, like, 50 degrees Celsius water, and it washes right off. But also with, like, isopropyl alcohol, you can get rid of it at, like, room temperature. So yeah, that's sort of my criteria for why I use this, is just it's very easy to clean off the board. And even the pale yellow version of this does an okay job of, you know, like, doing flux things, which basically the reason you use flux when soldering is it removes oxidation and it shields the solder from oxygen in the atmosphere so it doesn't start oxidizing again. And the reason you want to do that is that the oxide, like, when you're, you know, soldering, the tin oxide is not really what you want to be using to connect your electronics to, like, your components together. So that's why you use flux when soldering, because if you don't use flux, the top, like, basically the top layer of the solder will start building up tin oxide very quickly, and you basically end up with very crusty solder joints because tin oxide is kind of terrible. So yeah, as also, like, copper oxide is, you can't solder to copper oxide either. So I might actually do a demonstration of, like, what happens if you heat, because if you heat up a copper plate to, like, a high temperature, it'll very quickly build up an oxide layer, and if you try to solder on top of that, you're not gonna achieve anything. But if you add some flux to it and then heat it up again, the flux will actually eat away the oxide, and you can solder to it just fine. So that's sort of the best demonstration of what like, why you want to use flux when soldering. Because a lot of people go always like, oh, you need to use flux, it makes the solder flow better. No, it literally just makes sure that, well, I guess not having, you know, a bunch of oxides building up does help with the solder flow, but it's because of the oxide. So it's like that's why your solder stops flowing, because you start getting oxide buildup on everything, because at high temperatures in an oxygen-rich atmosphere, you get oxides very quickly. Or if you just have some, like, joint that's been like some copper plate that's just been exposed to oxygen for a long time, you'll sort of have the same problem. But anyway, here, like, in this initial step, the flux isn't that necessary, because, like, this is copper that I literally, like, we've just scraped the solder mask off. There's not going to be really any oxide buildup. But, you know, the flux the flux just generally helps. So, and more, like, and especially since this is no clean and water soluble, it's like there's no harm in using more of it. So anyway, next step, adding some new copper plates. So yeah, basically after I scraped off the solder mask, I put just some blobs of solder everywhere, right? You can see we have some blobs of solder for the current sensing to connect to, a blob of solder for the power plane, and then over here you can see how that progresses. I basically attach a copper plate that connects to the power plane where I scraped away the solder mask, and then also connects to the current sense over here. And that's sort of my plan for the other side of the board, as well, for the other phase as well. Yeah, and at this point I realized that this capacitor over here is kind of a problem, because I decided that I'm not going to use hot air soldering for this process because the problem with like having these copper plates is that if I'm hot air soldering, once the board and the inductor get back up to temperature, right? Like let's say I was reattaching the inductors using hot air, like once the board is up to temperature and the inductor is up to temperature, like this plate is going to be free to move around. And if the plate is free to move around and you're like poking and prodding at the inductor that you're trying to attach, you run the risk that this current sense connection is just going to get disconnected, which would be really bad. And you know, like it would be annoying to diagnose that it's disconnected because you'd basically have to check that the current sense, like you'd basically have to go check the connection of the current sense at the actual controller, which is just kind of annoying to deal with. And so I decided that instead of, you know, having to deal with that and then potentially having to fix the current sense connection because like the plate moved, I decided that I'm actually just not going to deal with that at all, and I'm just going to do everything with the soldering iron because that way I don't run the risk of the plate being free to move around. Especially on this side of the board, that's actually even more of a problem because we are trying to solder directly to the pins of the SIC651, and yeah, all of these pins on this side of the power stage are actually the switch node. So I actually put a great big blob of solder over those just sort of to bridge them, and so that when I come in with the copper plate, I have something to easily make contact with. Anyway. So yeah, this is sort of how it's progressing, and I decided that this capacitor has to go because with this capacitor in place, it's going to be just an absolute nightmare to get the inductor installed. And this is a tantalum polymer bulk capacitor for the memory VRM. So the thing with these is that they're very easy to damage by like overheating them, and failing tantalum capacitors, like they tend to burn up when they fail. So I'm not putting this back on after I removed it because I don't trust it anymore. Anyway, so here's the next step. So you can see that I got rid of the capacitor, and that's just kind of that. And then I attached one of the inductors, and it's super crooked, and here you can really see why I wanted that capacitor out of the way, because like this is where that leg of the inductor is. Yeah, capacitor had to go. And the reason the inductor is this crooked is also because the DR-MOS component itself has some height to it, and I decided and so in order to get the soldering iron at this side of the connection, again, like the inductor just couldn't be straight because there just isn't enough space to get the soldering iron at the little pad that the inductor uses. I guess I could have extended the switch node a bit with more copper plate, but yeah, no, I really wanted a direct connection there. So yeah, that's what's going on with that. And then over here you can see the new switch node and the power plane extension. So yeah, you know, just solder that into place, and you can see that I've been just constantly adding more flux as I go along. Yeah, so now we need to get on the last inductor, which just ends up looking like this. Also very crooked. Again, same reason, is just like the DR-MOS component gets in the way of soldering the inductor into place. Arguably, if you wanted to do a neater job of this, it would have been best to like desolder the the DR-MOS component, then put the inductor in place, and then like hot air resolder the DR-MOS component again. But yeah, this is just like more steps than necessary, and power stages really don't appreciate getting like you basically want to not heat components as much as possible, right? Like I don't think they would kill the power stage to like take it off and put it back on again, but it's better if you don't do that in the first place. Because yeah, the components aren't really designed to last long periods of time at like soldering temperatures. So anyway, yeah, so now both of the inductors are on, and we just need to take care of the capacitor problem. And the capacitor problem ended up being solved with this 1200 microfarad 2.5 volt Nichicon FP cap. Originally, I wanted to use a pair of 560 microfarad caps just because the original capacitor was a 680 microfarad tantalum polymer. So that would have lower ESL than any through-hole capacitor that I have, any through-hole capacitor ever made. Just through-hole capacitors inherently have more equivalent series inductance to them, which is just makes them just makes them worse at filtering, switching noise and transients than tantalum polymer capacitors. But the thing is, and so one of the ways you can sort of work around that is to just use more capacitors in parallel, which is why originally I wanted to use a pair of 560 microfarad caps. But the problem is, there's not really enough space. Like, there really just wasn't enough space to attach those to the board the way I wanted to. And so I ended up using this 1200 microfarad cap because, like, the reason I went with 1200 microfarads was just like, well, let's try compensate for the inferior, ESL. The ESR is actually probably better on the aluminum polymers than on that tantalum SMD capacitor. Like, a lot of the funny thing is, tantalum polymers and aluminum polymers in the SMD packaging, if you get cheap ones, they're actually kind of horrible in terms of ESR. Like, you can get like 15 milliohm ESR, 20 milliohm ESR, 25 milliohm ESR, whereas this FP cap over here, this thing's 7 milliohm ESR, and that's not even the lowest ESR FP cap I have on hand. It's just this is a low ESL FP cap, so that's why I tend to use these, rather than some, I do have some 5 milliohm ESR FP caps as well, but those have like a larger casing, and so they have worse ESL properties, and so, yeah, I decided to use this one. It probably doesn't matter. Like, I probably really overthought my capacitor selection here. It's a bulk capacitor for the memory VRM. Who cares? That would be the main reason why, like, that tantalum is probably absolutely atrocious in terms of ESR. Yeah, like, I didn't really, like, I didn't want to unintentionally downgrade the output filtering of the memory VRM, and so I went like, well, I can't really get the same, like, ESL properties as the previous capacitor. We may as well go with, like, twice the capacitance. And that's really no problem. Like, the main risk you run with putting too much capacitance on a VRM is that it might not want to turn on because of the inrush current during soft start. But going from 680 microfarads to 1200 microfarads is not going to trigger that. I have accidentally run into that issue on a single phase VRM on a different motherboard where I added, I think, like 2,500 microfarads to it, and then it was upset. But this is, like, we are literally replacing a 680 microfarad cap with a 1200, so yeah, this is going to be just fine. And then the 2.5 volt rating is just because I do believe the board allows you to set up to 2 volts on the memory voltage. I've not checked, funnily enough, but most Gigabyte boards come with a 2 volt memory voltage limit, and so we don't really want to be using a capacitor rated for 2 volts, because while it would probably be fine, you're generally supposed to, like, your capacitor is supposed to be rated above the voltage that you're attaching it to. So for a 2 volt power rail, you would want to use like a 2.5 volt. For a like 1.8 volt power rail, you could use a 2 volt, but I'm pretty sure the board lets you go up to 2 volts, and so I decided to, like, well, also you can't really get aluminum polymers in 2 volts. Actually, no, you can. I don't know why you'd want that, though. There's really no, like, with the SMD capacitors, there are benefits of getting the 2 volt ones because they're cheaper and you can get them in really, like, you pay less for really low ESRs on the 2 volt models compared to the 2.5 volt ones. But with through-hole polymers, it's just like the 2 volt through-hole polymers exist. I'm not entirely sure why, because I guess they're slightly cheaper. But yeah, in terms of like capacitance or anything, the 2.5 volt caps are just fine. So yeah, I threw that on there, and this is sort of the main reason why I actually want to take an oscilloscope to the board, because I'm not, like, I really don't think this I don't really think this caused any issues. I'd be very, very surprised if this caused any issues. But I want to be certain, right? And just kind of winging it with like, well, generally memory VRMs don't really need to be that fancy, and the cap is bigger than the original one. It should be fine. Is not good enough. So I do want to take an oscilloscope measurement just in case. And also I did try to like half-ass an oscilloscope measurement from the top side of the board with a 10x probe. But the problem is, if you try to measure anything in close proximity to a VRM, you can't measure anything because you just get a bunch of switching noise, which was rather frustrating. Because yeah, like I tried to, because you know, like you have like this great big ground pad over here and this memory VRM, like the memory power plane right over here. So I was like, oh, I'll just shove the oscilloscope probe onto these two pads, and I'll get a measurement, and it'll be great. Like I won't have to go through like connecting the probes properly. But when I did that, I was getting just a ton of noise on the measurement, and I'm pretty sure that's just because we're right next to the inductor. Yeah, these things radiate a lot of switching noise. So, yeah. And that's why I plan to basically, like, I need to take the board apart, get the backplate off, and actually maybe I could take the voltage measurement at the CPU socket. We'll see. I've not really looked at the back of the board since I fixed it. Anyway, so, yeah, that's the sort of final stage of fixing the board. And here's the board in all its resurrected glory. And this photo, unfortunately, is completely out of focus on the part where I actually did all of the work. For some reason, it's focused like here. Because even here, like this is blurred too. But yeah, so that was a really like easy fix. Right? Like there wasn't a ton of like thought that went into it. It was just kind of like, well, need to somehow rebuild the switch node, reconnect the current sense, put the inductors back on, and then like the capacitor was just kind of like, yeah, I have to deal with that. I'm not like I still kind of feel like I might end up messing with the capacitor configuration over here because this just kind of looks a bit ugly. Like it's really not a big deal, and performance-wise, it's probably just fine. But I don't know. I mean, the inductors are literally lopsided. I'm not sure what I'm so worried about. Like, straightening out that capacitor somehow. Like, the annoying thing is there's just not much space for maneuvering with the soldering iron, right? So that's why that ended up the way it did. Yeah, I'll probably just leave it. Because I don't really think this is too much of a problem. It's just kind of ugly to look at. Anyway, yeah, so that's that. Oops. Evidently I hit something on the mouse and reset LinPack. Good job, me. So, yeah, that's it for the video. The board runs. I don't have any use for it, but hey, it was fun to try fix it. Now it's just like oscilloscope measurements, and maybe I'll do a video about the memory overclock on this board. So, yeah, that's it for the video. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, stickers, posters, the usual YouTuber merch. I also have a Bandcamp if you hate your ears. So, yeah, there's a link to that down in the description below. And yeah, Teespring, Patreon, Bandcamp, they all help out immensely with running the channel, mostly because they fund my addiction to non-functional hardware. So, yeah, if you check them out, that would be much appreciated. And that's it for the video. So thank you for watching, and goodbye.